Good afternoon to everybody. We are here for the April session of the SIFS Young Seminar organized by the Italian Society of Statistical Physics. As usual, we have two speakers, and the first one is Ivan Di Terlizzi. Ivan got his master degree in 2018 at the University of Padova, working with Marco Baiesi on thermodynamic uncertainty relation. Then in the same university, he got the PhD 2 years ago. And since then, his postdoc in Dresden at the Max Planck Institute for the Physics of Complex Systems. And now he is going to give a talk entitled Variance Sum Rule for Entropy Production. Okay, Ivan, please.
Thank you, Paolo, for the kind invitation. Good afternoon, I'm Ivan Di Terlizzi, and today I'm going to talk to you about my my PhD project, which has kind of been completed during my my first year as a postdoc in Dresden, and its title is Variance Sum Rules for Entropy Production, which is kind of an obscure title, but I will try to explain to you what we mean by variance sum rules. So first of all, the framework and the purpose of this work. So what we are going to do is basically to take a system which is in an non-equilibrium state, such as this, and we will put it in contact with a probe, and by measuring the oscillations and the traces of these probes, like this one, we are trying to infer the degree of non-equilibriumness of this system. We also assume that the system can be modeled by a Langevin equation, like this one, and by using the framework of stochastic thermodynamics, we will estimate the degree of non-equilibriumness of these systems by means of the famous entropy production. In this case, is actually an entropy production rate, because we are in a non-equilibrium system, which is nothing else than the sum over all possible heat baths in contact with the system of the heat exchanged with these systems divided by its temperature. So the strategy that we are gonna exploit is based on a result, which is indeed the variance sum rule, which can be obtained from the Langevin equations in a very simple way, actually. And as you can see here, we have on the left-hand side the sum of two variances. So this is why we call it variance sum rule. One of those is the variance of the displacement, which is something that is usually always experimentally obtainable, because we have indeed traces, plus the variance of the cumulative forces, which is actually the term which is more problematic to estimate, as I will show you in the later slides. So the sum of these two variances equals a linear term, which is proportional to the diffusion matrix. So just to fix a little bit of ideas, is this line here, plus a term which we call excess variance, which is different from zero only out of equilibrium. So a possible scenario with a variance of the position plus a variance of these cumulative forces could be this one. And as you see, out of equilibrium, we would observe this humpback, which indeed indicates that the system is out of equilibrium. So why is this interesting? The main reason is that this excess variance not only is different from zero out of equilibrium, but its concavity, its curvature equal at zero, is actually linked to entropy production rate. So this allows us, by exploiting the variance sum rule, to express the entropy production rate in terms of the second order derivative of the displacement, which is something, it's not, so I will show you how in experimental situation this quantity is not extremely trivial to estimate, but it's also not extremely difficult. So it's something which is experimentally obtainable. Plus the variance of the forces. The competitors to this formula is the formula which I showed you in the first slide, which is the formula by Sekimoto, which also requires the same amount of information as here, which means positions and forces. But as I will show you, it will turn out that sometimes this formula gives better results, especially when the moments where entropy production is produced are few with respect to the total amount of time in which the system is evolving. To give an example of what I'm saying here, we consider a system which is a stochastic Zwickschen trap. So we have harmonic potential whose center is jumping stochastically between two points, and with some rates, which could be called V plus and V minus, W plus and W minus, sorry. And the most important thing in this case is that this system is actually easy to create experimentally, so to make it real experimentally. And this is indeed what has been done. So we considered, in this case, I show you 3 possible realization of dynamics of this system. So these 3 ones, all have been done at VW tot equal to 20 Hertz. But what we have changed here is the distance between the 2 centers, so this delta lambda here. We verified the variance sum rule and so on. So these are 3 possible realizations. There is no fitting here involved, so everything is working. Here is also a possible example of how these 2 variances add up to the expected value of the total variance. And again, this is interesting, but what is more interesting is the entropy production estimation, which comes from the variance sum rule. So in particular, I show you one example, which, of course, by honesty, I have to say it's the best example that we have, where we have this jumping rate of 20 Hertz and a distance between the center, which is equal to 280 nanometers. And as you see, the entropy production estimated for these many traces gives an average entropy production estimation, this red line, which is very close to the real value, which can be estimated analytically. It's not exactly the same, but what makes me more happy, to be honest, is that by trying to estimate it by the formula by Sekimoto, we get a value which is basically the half with respect to the real one. And again, a possible reason why this happens is that the events where entropy is being produced are exactly those where the system jumps. And these events are much less with respect to the, let's say, to the total time that we are considering. And hence, this estimator of entropy production is not so good at getting these events. Just to show you that this also works for other possible realization of this experimental setup, show you that for delta lambda squared spanning 3 orders of magnitudes, our estimator is a good estimator of entropy production. So here I didn't have time to add the estimation of given by the Sekimoto's formulas, but in these 2 cases, it's a worse estimation, whereas in this case, it's a better estimation. So I wouldn't claim that it's a better strategy with respect to using the usual formula, but it's a valid alternative, especially in these kind of situations where, as I said, the events where entropy production is being produced are few with respect to the total time of the system's evolution. But the problem here is that, as I told you, most of the times the forces which are acting on the probe particle are not experimentally accessible. So in the meantime that experimental techniques in order to make this possible are being realized, we have to think about a different strategy to estimate entropy production by using variances, which does not involve the direct measurement of the forces. So what we came up with is a strategy where basically we take the forces and we split them between a force which is measurable, which usually is the forces which the optical tweezer or the experimental setup is exerting on the probe particle, which is usually measurable, plus an interaction force, which is something which needs some kind of modeling. And once we get this reduced variance sum rule, where on the left-hand side we have everything that is measurable, and on the right-hand side everything that concerns the modeling, we can use this formula to fit the model, get the parameters, and then eventually estimate entropy production. So a first way to see whether this strategy works or not is to take the previous experiments done with the stochastic switching trap and see whether the parameters, which we know are being fit in the right way from this strategy. So again, we mimic that the forces can be split into a part which comes from the optical tweezer, which is this one, plus a part which is actually the part that puts the system out of equilibrium and is actually the forces that are exerted on the particle when the trap jumps. So we make it so that we don't know this part here, and we do all the calculations. We know that this reduced excess variance is equal to this. We do all the calculation and so on. We do the fittings, we perform the fitting strategy, and as you can see, the right-hand side, this one, which are the continuous lines, are actually fitting very well the left-hand side, which are the crosses, the squares, and the circles, for different kinds of delta lambda. So once we have convinced ourselves that this strategy is actually robust, and it is, we decided to challenge ourselves to try to estimate how much entropy is produced by some biologically relevant system, such as red blood cell. So red blood cells have been studied a long time. In particular, the flickering of red blood cell has been studied, and there are proofs in literatures that in literature that claim that this is actually an active system. So the strategy in this case will be to consider model these fluctuations. So this is a possible realization of a red blood cell attached to a pipette and to a probe, which fluctuates and gives a probability density function and traces which can be analyzed. So the first thing that we have to do is to model the force and split it into a measurable part, which is the deterministic force part, which has a contribution by the force coming from the optical tweezer, plus a contribution coming from the elastic part of the red blood cell, which means that we get a total stiffness, because these two springs are in parallel, and these will imply that the variance sum rule will have this form here, where for the moment we have not specified the force that puts the system out of equilibrium and is included in this term here. So for the moment we have that on the left hand side everything is measurable. We have some parameters here which have to be fit. A first guess for this force, the active force, is to take an active Ornstein-Uhlenbeck. So this force has its equation of motions and is not coupled to, so the coupling between the degree of freedom x and f is non-reciprocal, which means that the system is indeed out of equilibrium. So this system is also equivalent to taking an active force, which is exponentially correlated. So we have memory and all kind of stuff. And what we have to do is to fit this model in the same way we have fit the stochastic switching trap. And then once all the parameters have been estimated, we estimate entropy production by using the estimated parameters and putting it into the analytical formula for entropy production. So everything sounds well, at least I hope so. But in this case, the thing does not work. And the reason is that what we do basically is to take this red blood cell here, we pull the red blood cell at different forces and we gather traces at different forces. And what we see here is that the stiffness, which is the sum of the stiffness of the optical tweezer and of the red blood cell, is not stable while the forces are being increased. And this is not reasonable because the intrinsic stiffness of the red blood cell has been measured in other experiments and it's almost constant. So this increase, it's not good. Also, the typical time of the activity is too small with respect to other experiments that have been performed. So what we came up with is a more complicated model, which is a two-layer model with a hierarchy, where basically we think that the good way of modeling this system is to think about a passive membrane given by this K int here, appearing here, which is actually put out of equilibrium by the cytoskeleton inside the red blood cell, which is actually the thing which is out of equilibrium, and is put out of equilibrium again by an active Orsay-Uhlenbeck noise. This is also inspired by other works which claim that is actually the cytoskeleton, which is the part which drives the system out of equilibrium. Again, we can put everything in the variance sum rule. This term here becomes complicated now. But what we can do is to fit all the parameters of this model and then put the results into the analytical formula for the entropy production and try to see what happens. So two possible experimental setups where we tested this strategy are these two possible setups are with optical tweezers. The first experiments have been performed in Barcelona by Marta Gironella, and this one has been performed in Göttingen by Timo Betz. It's a slightly different setup, but the idea here is that we have traces, in this case at different pulling forces, and here for healthy red blood cell and for starved red blood cell. In this case, it's 96 hours, I think. It was kind of cruel, but it had to be done in order to see whether our procedure actually sees activity where there should be activity or non-activity where the red blood cells are dead. And we fit everything. These are the results. So the total variances have this kind of behavior. But the most important thing is that for Marta's experiments, we have entropy production, which is around 20,000 kBTs, and it's kind of stable for the different pulling forces, as shown here on the x-axis. Whereas here, for Timo Betz experiments, what we have is that for these different red blood cells, active red blood cells, we get around 6,000 kBT of entropy production, which is actually compatible with the amount of entropy production estimated by Timo in another experiment, in another paper, with the same experiments and using the violation of the fluctuation dissipation theorem as a tool to estimate entropy production. Instead, for starved red blood cells, as you see, entropy production decreases by an order of magnitude. So this is a good sign that actually we are measuring something which makes sense. Another possible setup that we consider is actually here there are no probe particles, but the system is still describable by the equations which I showed you some slide ago. And basically what has been done here is so Diego and Paco basically took a red blood cell and they traced for every point, for 512 points around the surface on the red blood cell, they gathered traces, and for healthy red blood cells, and in this case for dead red blood cells, not only starved but dead. Again, it's sad, but it has to be done for science. And by analyzing these traces again with the same algorithm, what we get is a entropy production map around the whole surface of the red blood cell. And as you can see, again, the order of magnitude for the healthy red blood cell is around 10 to the 4 of kBTs of entropy production, whereas for the dead red blood cells, it's around 100. So still we get comforting results. And another interesting thing here is that we can measure a correlation length for the entropy production field, which is around 0.4 micrometers. To conclude this discussion, what we have to do is to estimate the total amount of entropy production which is produced by the whole red blood cell. And to do so, we have to imagine entropy flux, which is exiting a unit surface. And in order to estimate this flux, we have to divide the estimated entropy productions, which I showed you before, divided the area, which is actually the area which we are measuring in some sense. And the total area is this amount, is this quantity here. It's, I think Felix Retort did this calculation. And regarding this area here, which we have to divide the entropy production, we take a geometrical unit, which is the circle, because it's the most reasonable thing to do. And in order to get this quantity, we actually have to estimate a typical radius. So what is this radius? In the case of the optical tweezer stretching, this can be estimated by some fancy data science techniques. And it turns out that it's around 1.1 micrometers. Whereas for the ultrafast optical microscopy, we take an average between the typical correlation of the traces and of the sigma field, and it is around 0.6 micrometers. Regarding
5 minutes.
Okay, I'm perfectly in time. Thank you. So once this radius has been estimated, what we can do is we estimate this area, we get the flux, we multiply the flux by the total area, and we get the total entropy production that is being produced by the red blood cell. And finally, by doing this, what we get is that for all three experimental setups considered, we get that the total entropy production is actually the same order of magnitude of what has been obtained by bulk calorimetry experiments, which has been performed, I think, like 40 years ago. So basically, they took this lot of red blood cells, they put them in a box, they waited some hours and looked how much the temperature has increased in the surrounding bath, and by that they estimated how much heat these red blood cells are producing, and it more or less turns out to be the same values that we are getting with our strategy. So to conclude, I have showed you two possible techniques to estimate entropy production. The first one concerns the situation where forces are known. And in this case, the variance sum rule offers a new method to estimate entropy production in a model-free way, in the same way Sekimoto did, but it has its computational advantages, so to say. When the forces instead are not known, we use this reduced variance sum rule to perform fits in a very robust way. I didn't tell you about this, but usually you could use the variance of the displacement as a fitting target, but using it in combination with the reduced variance sum rule actually increased the robustness of the fits a lot. And what we get for red blood cells is that this sigma map, this entropy production map around the surface, actually offers us the possibility to estimate this correlation length of the spatially varying sigma field, which is a main prediction of active field theories. And also, we managed to find a correspondence between our estimates of entropy production and those coming from bulk calorimetry, which is a totally different approach. Plus, this may suggest that the heat produced in the glycolytic pathway is tightly coupled with the membrane flickering, and which is something which is not trivial at all, I think. but I don't know why it should be like this, but it turns out to be true. So at least for the moment. So, and with this, I would like to conclude. Thank my collaborators, my supervisor Marco Baiesi for his patience, for Felix and Marta, with which we started the project, and new collaborators which joined us in the last year, and of course you for your attention.
Thank you very much. Thank you. Thank you, Ivan.
Thank you.
So we have a few minutes, for questions, comments. Okay, I will start with a small question. What about the hypothesis about the force? I mean, it is sufficient that the force is such that the system is driven towards a non-equilibrium steady state. Is it enough?
So the thing is that, of course, we would like red blood cells to be active because our aim is to estimate entropy production. So but in this case, you see, the system may be at equilibrium. It just the only thing that should be equal to 0 is this epsilon here. So once you set epsilon equal to 0, the system is at equilibrium, and actually for dead red blood cells, we fit epsilon very close to 0. Instead, for systems out of equilibrium, we actually see that this epsilon, which quantifies how much the system is out of equilibrium, is very far from 0. So, and of course, the system must, the model must be kind of based on the physics of the system that we are considering. As I showed you, the simple ansatz didn't work well for many reasons. Then we came out with this solution, which we worked a lot to convince ourselves that everything is right, because many of these parameters are actually linked to other experimental values, which are comparable to what we find. Of course, I cannot claim that this model is the truth, because of course this is first of all, the system is not one-dimensional. There are torsion, tensions, and so on. But for the level of simplicity of this model, I think we can actually describe a lot of physics, even if the system is simple. But of course, it's not complete depiction of reality. This is not,
Sure.
of course, not true.
Okay, there is a question by Achille.
Yes.
Hello.
Ivan, so I was wondering whether it's possible to do a real inverse problem in this inverse procedure in this, in the sense that, you start with experimental data, and you try to obtain by some sort of inverse procedure to try to obtain the parameters that that are in the model. So rather than a fitting. This is a real, I mean, something that has been done in the past for other, problem related to Langevin equations.
Okay. I've never heard it, to be totally honest. So what would it be?
So the idea is that you start with an experimental problem, and then you define some sort of score functions that you try to minimize it.
Okay.
In such a way that you get the parameter from the parameters of the model from the experimental data.
Okay, again, I didn't know about this. So I would like to add that I started as a theoretician. My PhD started as a theoretician. Then I ended up doing data analysis. So I actually learned to do fits in a good way in this project.
This is a theoretical procedure. It's not a brute force. I mean, there is a. Okay, maybe okay. I can.
Thank you for the suggestion. I will look it up because I don't know what I don't know this technique.
Okay.
But thank you.
Okay, is there any other question? Okay, if not, let's thank Ivan again. Thank you, Ivan. And